The electric field, we're going to try and describe it quantitatively and give you a visual picture, even though its reality goes quite a bit beyond any simple description. We describe its strength in terms of the force that it applies to a charge, and it's simply force per charge, the electric force acting on a charge. So the force per unit charge is this fundamental definition. Just like gravity can be defined as gravitational force per charge. Units, newtons per coulomb, that come right from there. Newtons over coulombs. Now an E field is a vector. So the total E field at any given point in space is the sum of all the individual E fields acting at that point. And so we're going to actually do that from the existence of several charges here. So there's charge 1. And it produces an electric field pointing toward it. Now what's the deal with the direction? The direction is simply the force on a positive charge at this location. So if this is producing an electric field, the field that it produces is in the direction of force that it would apply to a positive charge, and of course that's toward, since opposites attract. All right, so here's a positive charge and it will be away. So at this P here, at this point, the electric field is pointing away, and it will be larger, assuming these are of similar magnitudes, because it's closer. So there it is. It's actually an inverse square law. And then there's the third charge, closer than charge 1, and so it's bigger than that electric field at point P. And charge 4 produces an electric field like that. So these aren't super quantitative, but they would be by applying Coulomb's law. And then really just Coulomb's law divided, for force, KQ over R squared, and this Q would make one of those Q's go away. So it would be, the electric field would be KQ over R squared. All right, so if we add the vectors, it looks like this. There's number 1, and then tail to tip, number 2, number 3, and number 4. They can be added, of course, in any particular way. And then the result, like we've done in the past with vector addition, the total E field at that point. That's enough said. Simply, the electric fields add from all the point charges. Force field interactions. We have a positive and a negative. So to visualize it, we see the field going across like this, and from plus to minus. Now, at different angles coming out of here, they start and end on the plus and minus respectively. So that's going to be true for all of it. Here, let's go a little faster here. You can kind of see what's going on. There it is. The line spacing between all these visual representations is a measure of the magnitude. So when it's stronger, they're closer together. When it's weaker, they're further apart. So that's what the spacing represents. Now let's look at two similar charges, or the same sign, namely negative in this case. And now we will notice that there is a significantly different look. Okay, kind of sounds a little eerie there. And you'll notice that the E field lines, instead of seeming like they want each other, they're attracted to each other almost. They butt up against each other. And in fact, if you map these out with very carefully, you will discover that there's no place where these field lines actually cross. So they diverge from the positive, converge, terminate on the negative. For same charges, no lines ever intersect. And this will all be consistent with the force that will be acting on a charge in any location that the E field exists, whose magnitude is represented by the spacing between lines and the direction as shown with these little arrows.